Hi everyone, I'm Sarah. Today I will talk about Diel variation in the upper layer by a physical process using a BGC-Argo in the Bay of Bengal. The ocean is one of the most important ecosystems for biological productivity. Phytoplankton are the main primary producer in the ocean, and their growth depends on the sunlight. The sunlight change we call Diel variation, and the sunlight change they can cause the different response to phytoplankton, and such as photoacclimation and vertical migration, and we'll talk later. And our study is in the Bay of Bengal. The previous paper, they show physical and biological factor change not only daily but also seasonally. However, past data too sparse to capture daily changes. So we use the high frequency BGC-Argo flow data to study the Diel variation. And this map is the bay in the Bengal. And we can see in this have many color dots. And it's the float. And our study, we use the red dot, and you can see here, it can measure lower 12 hours every. So we use the BGC-Argo float as our data source. These floats are part of a global ocean observation system, and we choose the float. It can measure every 5 hours, and it can measure temperature, salinity, and chlorophyll, and dissolve oxygen. And we use the date from August 24 to September 23, 2015. And the float, it can down to the 100 meter. But to keep our system, to keep our data consistent, we use the above 80 meters for analysis. So when we get the data, we need to remove long-term change to extract Diel variation. In the study, we also use the sphere drop model, and it can show if light limits phytoplankton growth. Simply put, the sphere drop model tells us how deep light goes in the water and whether phytoplankton can grow in the whole mixed layer. So it can help us understand the daily change in the chlorophyll. In our results, and it's the float trajectory, and this is the profile of the all parameters. And this is bigger one. And now I will talk the layer depth. So I use the temperature for example. Here, we can see this picture have a black line and blue line. Black line is the mixed layer depth, and the blue line is the isothermal layer depth. And it means the depth where the temperature is 0.5 degree less than the surface. Okay, so now we look at the float trajectory. The float moves with a clockwise eddy when it enters the cyclonic eddy. When the float enters cyclonic eddy, upwelling happen. So this brings deeper water to surface. So the isothermal layer depth becomes shallow and affect the mixed layer. So I just we get the data. Now we convert the data. Convert the data to the Diel variation. So next, I will talk Diel variation of biophysical parameters. One is temperature. We can see it have lowest at 7 a.m. and increase have a high temperature at 5 to 6 p.m. This is because sunlight is strongest at noon. The ocean keep absorb the heat, so temperature peak later. And the chlorophyll, we look at the main chlorophyll. It's have a lowest at 6 a.m. and increase have a highest at 6 p.m. and the surface at 10 depth. We can see its morning is decreased and the lowest at 11 a.m. and increase have a highest when 7 o'clock. And we also can see the mean chlorophyll is more than the surface chlorophyll. So there are the main measure. One of the there are the two major reasons. First is photoacclimation. At noon, sunlight is very strong, so phytoplankton reduce their chlorophyll to protect themselves. They do this to avoid damage from too much light, which is called photoinhibition. Even though chlorophyll decrease, photosynthesis can still continue. And next is the vertical migration. Phytoplankton can move down to deeper water during the day. This helps them avoid strong sunlight near the surface. At the same time, they can get more nutrients from deeper layers later. When light becomes weaker, they move back up. So, an important point is lower chlorophyll at noon does not mean fewer phytoplankton. It means they are adjusted or moving in response light and dissolve oxygen. And we can see it's increased from morning to evening. It's similar like temperature. Yeah, same. And the dissolved oxygen increase because it is mainly controlled by photosynthesis. And we know higher temperature cause higher temperature reduce the gas solubility. But there, the photosynthesis is main. It's more than the temperature effect. And the salinity and mixed layer depth do not change much during the day. So you can see the ocean is stable in a short time. And finally, we use the third drop to analyze our chlorophyll. And this is our result. The depth at which chlorophyll can grow is much greater than the depth of the mixed layer. We can see here, it's more than 200 meters. And our data only 220 to 40. So it suggests light is enough for phytoplankton growth. And this picture say the chlorophyll is highly related to about 14 hours of accumulated light. And this picture is critical depth and chlorophyll. The two lights is same, so it suggests that chlorophyll variation is controlled by light. So we can conclude in the study we demonstrate solar radiation is primary driver of the Diel variation in the ocean. Temperature, chlorophyll, and dissolved oxygen are all response to change in sunlight. The decrease in surface chlorophyll during noon is likely due to photoacclimation and vertical migration. The study also highlights chlorophyll is not an immediately respond to sunlight, but rather reflect, accumulate light over time. Overall, this research provides new insight into the daily dynamic of ocean ecosystem and highlights the importance of high-frequency observation. Understanding Diel variation is important because it improves our interpretation of ocean productivity and biogeochemical cycles. Thanks.
Hello, Sarah. I think your presentation is splendid. I really love it. And I want to ask that, why is there no daily variation in salinity?
Salinity change is typical large scale. So in a short time, it can show that change.
Okay,
Yes.
thank you.
Can you tell me why you talk about MLD and ILD?
The MLD is the mixed layer depth, and ILD is iso layer depth. It can show the vertical structure, and we can see the light through it, light in the ocean how long. So it can help us explain our explain the chlorophyll. Yes.
Thank you.
Can you tell me what does the accumulated 40 hours of light means, and why did you use it?
This 14 is use the silver drop model. It accumulate something formula. So its results we can see the chlorophyll. You need to accumulate 14 hours here. 14 hours. They need time to store their energy to change to the chlorophyll.
All right. So the good thing about her presentation was, you can see that she was very fluent, and she used pointer very often. That's good, and she was very active. You can see like this, and with punctuation in her tone. So you feel that it's a very energetic talk. That's a very nice stage performance. But of course, there's place for you for improvement. So the first thing is this one is good. So add some small icon to improve her, to enrich the slide. And here you introduce the BGC-Argo. Could you please next time explain this a little bit clearer? It's not very clear to me. I read the paper, I know what it is, but maybe it's better to explain to them in a better way next time. And this one is good, showing the BGC-Argo. Okay, so the Sverdrup model is a little bit confusing, but I actually think maybe you can only show, like my suggestion for the previous speaker, you say you have this model, and maybe you explain it before you tell us the data. Because it's already 13 slides later when you talk about this model, and we no longer remember what it is. So you can only sort of tell them, we have this model, and later you introduce the detail. Good. And here you show this. This is nice. You have this animation, so it's very active. And we see, oh, and you have this, and it's good that you show the correspondence between the spatial distribution of the Argo and then the time series of the Argo. Is very helpful. And you also have them together. That's very nice. And then later, you were quite quick from here to this, because you see it's totally different kind of ways to look at the data. So I think during this transition, you need to tell us what was done from this kind of data to this kind of data. You need to spend a little bit more time explain this, because later you focus on this kind of data, right? And then starting from this kind of, from these slides, you have many of them, it's clear to us what it is, but it's not clear to us what is anomaly. We don't know what is anomaly. So next time, please explain it. And then, and here, you not only have anomaly, you also have this red dashed line. And I don't know what's that, why you have this red dashed line. Please explain us next time. And also, you need to explain what's the difference between the left one and the right one, where you have mean chlorophyll. What does it mean by mean chlorophyll? Why do you need to have two chlorophyll data to look at? And then, because you spend quite some time explaining chlorophyll, and here you focus on these two important reasons why they have this data. I don't remember, do they have solar irradiance data in their paper like this, where solar irradiance was highest at noon or 2 o'clock, 2 p.m.? Do they have that? Solar irradiance, 就是太阳辐射. Do they have that? It would be helpful to show the solar irradiance, where is the highest peak, to show data for this region. Okay, because it's southern hemisphere and I don't know which latitude, but it would be good to have data if the paper has. And okay, and dissolved oxygen is also okay. Okay, then here comes the bug. So, so first of all, please explain the detail of the model here. And it's very courageous of you to show so many data for this model, because I have no idea what is this. And I don't know why you have curve like this. So next time it's your duty to explain well. Why? How? What is this first? And then why do they look like this? Because when you present it, you always go directly to the interpretation. But we don't know how you come from here to here. And my understanding is this is only for comparison, right? The key point is here. So you need to explain this well. And this is another bug, right? So apparently, because think of their question, and especially you talk about, so first of all, you need to tell us what is the x-axis here. Apparently, this is not day in the time of a day, right? But because they are put together, it's easy to think of this as time of day. So you need to explain this. What is this exactly? And what is this exactly? And apparently you have this 14-hour because the 14 here has the highest value, right? Am I right? And apparently they do something for the ZC data so that they match together, I think. I don't know. I think they use this 14 to do something so that at the end they match together. So this is a 14-hour average. So next time you need to explain them well if you want to say so many about Sverdrup model. Good. Okay, so the the conclusion, is that conclusion already? Okay, it's good, it's specific, but at the end you say a little bit more. I think it's not that necessary, and you should use the time to explain this model well. Okay, good. Hope to see your improvement. Thank you, Sarah.